we have already established when can we say that a certain set, let's say set G, is a group under a specific binary operation. First and foremost, we know that for a certain group to be called group under a binary operation, the first one is the binary operation is closed. I mean, set G rather. Okay, set G is closed under binary operation star. Some references do not consider this as the first condition for a certain set to be called a group. Some considers this, but it's also important for us to really take note of this, because this is the first step before identifying whether a certain set is a group or not. The second one is that there should be associativity. Okay. Associativity. Let's talk about associativity of your binary operation, still using the given set G. Okay, that's the second condition, which is of course G sub or G1 for the conditions or the actions for a certain set to be called group. The second axiom, or G2, is actually the existence, okay, of identity element in of star, okay, of your star. And take note that this is actually true for all x's in a certain set G. Okay, this is our G2. This means that we only have, of course, we already established that as well, that we have only one element, identity element rather, and that is also true for all x or other elements in G. And then for our G3, which is the third axiom for a certain set to be called a group, we actually have here existence of inverse elements. Okay, elements. And this is actually for every, okay, so inverse elements x prime for every x in G. So difference between identity element and existence of inverse element is that for the identity element it is true for all, but for the existence of inverse element it is true for every element there exists or there must exist a inverse element. So these are the four conditions if you're considering closure property as one for us to be consider whether a set G is a group under a set operation. But the point here for this video is talking about Abelian group. When can we say that a certain group is Abelian? Pardon for a very lengthy discussion, because we need to establish this, because these are set of conditions that should be met. For Abelian group, first and foremost, we should know that it is a group. Hence, we have these conditions and actions. Now, for it to be considered Abelian, we have here the commutativity. Okay, commutativity of your operation star. The presence of commutative property allows the group to become an abelian group. In short, an abelian group is a commutative group. So say for example, if we have here, say for example, let you will have A and B element of your G, then you can establish that A star B is equal to B star A for all, okay, elements of A and B in the set G. So again, this is the only additional condition from a group to be added to a group to be called it an abelian group, the commutativity or the commutative property for it to be considered as a set to be a group. So again, we illustrated first the conditions for a certain set to be called a group, and then adding commutativity to be called abelian group. We might have some examples later on, presentations or illustrations for a group, or specifically abelian or commutative group. Thank you very much for watching.